Okay, today we're going to be looking at variance and standard deviation. So up until now we've been looking at the mean and the mode, the median and the interquartile range. So we've been looking at also the problems that some of these things have in our analysis of data. It can be useful to, say if you've got the mean, to see the average distance the data takes from the mean. And that can give us a indication of the spread of our data. So we call this the mean absolute deviation from the mean. And it's calculated by the sum of, I'll explain what this symbol means in a minute, the values x minus the average, the mean, over n. Now this here means you to calculate x minus the mean, and then you remove any minus sign, so you make that positive. However, when we do this, to calculate this accurately or efficiently for large data sets, it can be quite difficult. It's also not very useful for doing algebraic work with it. So we actually don't use this very often. Alternatively, we find the squared deviation, which is also known as the variance. So the mean squared deviation from the mean. Which is also known as the variance. So the variance of x is equal to the sum of x minus the mean squared over n. So if we were dealing with data which was to do with length, the variance, so if it's length, that's in meters, the variance of x would be in meters squared. This is just for example. So to make it easier and to have the units the same, we'll more often use what's called the standard deviation. So the standard deviation of x is equal to the square root of the variance, which is equal to the square root of the sum of x minus the mean squared over n. Now what we can end up with is, let's actually get a new sheet up. So variance of x equals, we had it from, I'll write the full, sum of x minus the mean squared over n, which can also be written as the sum of x squared over n minus the mean squared, which is the same as the sum of x squared over n, that's a terrible sum sign, minus the sum of x over n squared. Something just to note, we often use SD of x to mean the standard deviation of x. Now, what is the standard deviation? What does it mean? So a low that's not low. A low standard deviation indicates that most values are close to the mean. And a high standard deviation means values are more widely spread from the mean. Now, if you think of a drinks machine, say the drinks machine disperses 400 mils of, say, coffee. If it's got a high standard deviation, because the drinks machine is never going to do exactly 400 mils every single time. If the standard deviation is high, you're going to have some customers who are going to be really unhappy because they're going to have significantly less than 400 mils. Some customers are going to risk getting burnt because their cup's going to be so full that they'll be in danger of spilling it. So let's just summarize what we have. So for ungrouped data, standard deviation is the square root of variance is equal to the square root of the sum of x minus the mean squared over n, which is equal to sum of x squared over n minus the mean squared, where the mean is equal to the sum of x over n. Now for grouped data, standard deviation is equal to the root of variance again, which is equal to the square root of the sum of x minus the mean squared multiplied by the frequency over the sums of the frequencies, which is equal to the sum of x squared f over the square root of the sum of the frequencies minus the mean squared, where the mean is defined as the sum of xf over the sum of f. Now we'll do some examples just to show you how you calculate these practically, what that looks like in reality. So for the set of 5 numbers 3, 9, 15, 24 and 29, find standard deviation and which of the 5 values are more than 1 standard deviation from the mean. So, firstly, variance is equal to the root of x squared, the sum of x squared over n minus the root of it, the sum of x over n squared. So what this looks like, we take all the values of x, so 3, and then we square it, then we're going to add 9 squared, add 15 squared, add 24 squared, add 29 squared, all over 5. And then we're going to minus this. So for this part, what we do is we add 3, add 9, add 15, add 24, add 29, all over 5. I'm going to get rid of that bracket. Then the answer to this we then square. So that gives us, when you work that out, you get 90.4. So the standard deviation is equal to the square root of 90.4, which is 9.51. So then for part B, we look at, so this here is equal to 16. Okay. So we take our mean, which is 16, and then we add 9.51, which gives us 25.51. And also we take our mean again, and then we minus 9.51. So that gives us the values. If you think of all the data sitting here, our mean is 16, and our standard deviation is everything, which is 9.51 in this direction and 9.51 in that direction. All the data that sits in this range is within the standard deviation. So 16 minus 9.51 is 6.49. Now we look at our data. So what values are out with 1 standard deviation? So the answer is going to be 3, and the answer is going to be 29. Let's look at another one. Find the standard deviation of the values of x given the following table. Correct to 3 significant figures. So we've got x and we've got f. 12 appears 13 times, 14 appears 28 times, and 16 appears 10 times. So we need to, we're going to use for this one, the equation, standard deviation is the sum of x squared f over the sum of f minus the mean squared. So let's get our values for x, which we know is 12, 14 and 16. Our values for f, which we know to be 13, 28 and 10. And let's now do it. We need to find x times f. So 156, 392 and 160. Now remember, so down here we're going to have the sum of f. Add all these together, we get 51, and here we're going to have the sum of x f. So adding all these gives us 708. And the final column we need x squared f, which is the same as saying x times xf. So we've got xf here, and we're going to multiply that by 12 to get 1872. This one will be 14 times 392, which gives us 5488, and this is going to be 16 times 160, which gives us 2560. And now we want to sum these. 9920. So now we can slot them into our equation for standard deviation. So the sum of that is 9920 over the sum of f, which was 51, minus, now the mean is going to be equal to sum of xf over the sum of f, so that is this, 708 over 51, and we'll square that, and that gives us 1.34. Now, something to point out here. If you were to use, when you work out the mean, and if you were to take it to one decimal, so this equals 13.9 to 1 decimal place. If we were to use this in our calculation, we end up getting a standard deviation of 1.14, which is an error of 0.2, or about 15%. That's significant. So when you're doing these, you have to put the full values in to keep the standard deviation accurate, because when you start rounding things up, those roundings get propagated through the equation and actually get inflated. So that's just a wee point to bear in mind. Let's do one more example. Calculate an estimate of standard deviation of the heights of 20 children given by this table. So we've got the height, So 1.2 up to 1.4 up to 1.5 up to 1.7. And then we've got the number of children, which is the frequency. 2, 12, 6. So firstly, we need to find the mid value. So the mid value for this one is going to be 1.3, for this one it's going to be 1.45, and for this one it's going to be 1.6. So next we need to take the mid value x, multiply it by the frequency, so that's going to give us 2.6, 7.4, 9.6, and then the sum of x of f is equal to 29.6, and the sum of the frequencies is going to be equal to 20. And finally we need x squared f is going to give 3.38, 25.23, 15.36, and then the sum of x squared f is going to give us 43.97. So now we just need to slot everything into our equation for standard deviation. That's meant to be the mean of x squared. So you get 43.97 over 20 minus 29.6 over 20 squared, and that's going to give us 0.0081, which, working that out, gives us 0.09 of a metre. So I hope that helps.